I'm JD Arnold. I'm doing electrical distribution, and this is my presentation for my teaching topics. Learning objectives of this presentation are to understand the types of currents and which one is most commonly used in buildings, which you should already know. Single phase and three phase power and how to calculate them. Learn how transformers work and the calculations that are related to them. What a power factor is and how it affects us, and grounding. There are two types of currents. There's a DC current, which is direct current, which is the flow of electrons that is in one direction. This is commonly found in computer power, phones, and emergency power. The second type of current is AC, or alternating current. This is where electron flow reverses direction at regular intervals. This is the one that you'll most commonly find in buildings. AC can be distributed at high voltages and can be easily transformed into a safer, lower voltage. Another thing to know about alternating currents is it is a power of choice for utilities. It is because it can be transmitted over long distances without excessive distribution loss, which is where it loses power through the lines. It can then be transformed into a lower, safer voltage going through a transformer. There are two types of powers that we'll be talking about: single phase and three phase power. So these powers are transmitted over high voltage transmission lines using three conductors. We use three conductors because utilities generate three phase power. This causes the current to flow between three separate conductors. Three phase current and voltage peaks are offset 120 degrees between the three phases. This is so nearly equal electrical loads are connected between all three phases. When equalizing the connected loads, the energy produced by the generators will be used in a complete and balanced way. When calculating these types of powers, you have the single phase power equation right here, which is E, or volts, times I, or amps, equals watts. For three phase power, you have E, or volts, times amps, or I, times the square root of 3, because this is a three phase power, and that will equal the total watts. Now we have the different uses of them. Residential neighborhoods usually have single phase power. The utilities will designate individual phases such as A, B, and C. This means it allows them to configure them to meet the needs of each house. If one neighborhood is connected to AB, then the next will be connected to BC, so they do not overlap. And then the final one will be connected to CA. This allows the total load to be balanced. There's no overlapping necessarily. They are both connected to all three neighborhoods are connected to different connections. The next of which is commercial and industrial electrical customers that use three phase power. They use these things called motors, which are generators operating in reverse, and commercial use in reverse. And commercial uses three phase power motors. They use three phase power motors because they are more efficient than the single phase power motors. Any motor larger than 5 horsepower is usually a three phase power. However, if three phase power is available, any motor larger than a half horsepower should use three phase because it is more efficient. Now we move on to power distribution. High voltages are what we consider up to 500,000 volts. These are used on major distribution lines. They do this because for a given electrical load, more voltage means less current. This means it will reduce the current flow, which reduces the transmission loss or the power loss just through moving the energy from one point to another point. Insulators on electrical distribution lines indicate the line voltage. The larger the insulator, the higher the voltage. Now, transformers. Transformers are unique and efficient devices without moving parts that trade AC voltage for current. Transformers permit power distribution at high voltages. This minimizes the line losses, like I said in the last slide, and allows the delivery of a variety of lower voltages for building services. It means it's going to delegate how much power is going to each building, and so each of them can have their own services. Transformers allow utilities to serve many customers with different electrical requirements for using a single distribution network, meaning they can all be in one thing and they'll sort it out and send it out. Here, I use the example from the book, which is residential customers may take 240 volts, while commercial customers may take 480 volts. This means they can use the same transformer and send out different volts and different power requirements for each building. I threw this next one in here. Large industrial plants may need up to 13,200 volts, which is quite a bit more than the other two. Now, transformer include an iron core surrounded by two circuit loops. These are called windings. There are two types of windings. There's a primary winding and a secondary winding. The primary winding is used for the high voltage or the input of the transformer. The second winding or the secondary winding is for the lower voltage or the output. Transformers change high voltage primary power into low voltage secondary power. This is done by a pulsating magnetic field that induces a current flow. Now, when we talk about calculating these, transformers are rated in kVA. The reduction of the secondary voltage is equal to the ratio of winding turns from the primary. A ratio of 55:1 was what was given in the book. This means when we have to get that voltage for the secondary one, we're going to have to divide by that 55 because that is the number of windings. We'll get to that in just a second though. To calculate the primary winding, the equation is volts times amps divided by 1,000. For a three-phase transformer, you would do volts times amps times the square root of 3 divided by 1,000. Now, to find the voltage of the secondary winding, you must take the primary voltage and divide it by the number of windings. This is where the ratio comes into play. The example I came up with is if you have 100 volts that was from the primary, you have to divide it by 10 windings. So I did a 10:1 ratio, which will give you 10 volts. Moving on to power factor. Power factor is an interesting topic. Transformers, motors, and all windings have a property called inductance. Inductance is the tendency to oppose changes in a circuit current. Inductance reactance is a tendency to resist changes in current flow. Inductance reactance is a characteristic of windings in an AC circuit. This results in a delayed current flow, so the current peaks after the voltage peaks. So basically what we're trying to do is make sure the current and the voltage don't peak at the same time. Now, moving on to the power factor and how it affects us, is the power factor is a number index used to quantify lagging currents, what we just talked about, how the current peaks after the voltage. A building with no motors or coils will have a power factor of 1. Now, to calculate real power of a building, you have to go amps times volts times PF, or power factor, which equals watts. That is for the single phase power. For three-phase power, we would go amps times volts times power factor times the square root of 3, which will give us our watts. Finally, we're moving on to grounding. Grounding means it is connected to the earth. We do this to dissipate faults and currents. A fault in a current is caused by lightning or equipment failure. We don't want this failure or lightning to overload our circuits and break them or anything like that. So that's why we ground them for safety measures. Grounded connections can be made to underground metal piping or copper-coated steel rod that is driven into the earth. We do grounding because utilities save money by using the earth instead of a conductor. If you have any questions, feel free to reach out. Hope you enjoyed my presentation. All this information can be found in your textbook, except for the cool pictures I provided.